Hey, everybody. So this is the first of two lectures in which we talk about the concept of a function being well-defined. In the first lecture, we will give several examples where things go right, and in the second lecture, we'll give a few examples where things go wrong and try to figure out exactly what is the criterion that makes things work. Okay, let's review something we've done a few times. Let's take the integers and let's define an equivalence relation where we say x is equivalent to y if and only if x is equivalent to y modulo n. Then it turns out that this is an equivalence relation. We proved this last time, and we've essentially proved it several times before in different forms. Let's think about what the equivalence classes of this relation are. As we showed before, that if I take any number r, the equivalence class containing r is a set of all integers such that x is equivalent to r mod n, or, as we've proved in the past, n divides x minus r. One can show pretty easily that the equivalence class corresponding to A equals the equivalence class corresponding to B if and only if A is equivalent to B modulo n, which is true if and only if A equals B plus kn for some integer k. All right, so let's think about the integers under these equivalence classes. Basically, think about the partition generated by these equivalence classes. We're going to call that set Z sub n. And note that there are n equivalence classes. This set has exactly n elements. There's the equivalence class corresponding to 0, corresponding to 1, corresponding to 2, all the way up to n minus 1. In a specific case where n equals 2, we get two sets, the evens and the odds. Now, let us define two operations on these sets. It'll look a little weird, but let's do it. So we're going to add these sets. And the way we add these sets is we basically add them mod n. So given the equivalence class corresponding to a number x and the equivalence class corresponding to the number y, we take x plus y mod n and look at the equivalence class of that number. Similarly, we do the same thing for multiplication. If we have x and y and we want to multiply the equivalence classes corresponding to x and y, we take the number xy and compute its equivalence class modulo n. Okay, let's think a little bit more carefully about what this actually means. To add two sets, we choose an element from each set, add the elements together, and then figure out what set that summed element lies in. Okay, so for example, if we're doing modulo 4, we say the equivalence class of 2 plus the equivalence class of 3 is the equivalence class of 5, which is 1 mod 4. Notice, however, we made a choice. We picked the numbers 2 and 3 from our sets, and then we added them, and then for that matter, we replaced the 5 with a 1. What we're doing is for a given set, we're choosing a representative and then operating on the representatives. But what we need to be true for all this to make sense is our choice cannot change the result. In other words, if we choose a different representative of each class, we should get the same answer. Or if we say this another way, we need to show that the set we end up getting at the end cannot depend on any of the choices that we've made. So let's make a definition. So we say that an operation is well-defined if it is independent of any choices used in the definition. And we're going to state a theorem that says that if we look at the operations, addition mod n, multiplication mod n, on the set Zn, these are well-defined operations. Now let's start the proof. What do we really need to show? We need to show that if x and x prime live in the same equivalence class, and y prime live in the same equivalence class, then x plus y and x prime plus y prime live in the same equivalence class. If that's true, then none of the choices matter, because I could pick x and you could pick x prime, and we get the same answer. Said another way, we need to show that if x is equivalent to x prime and y is equivalent to y prime, then x plus y is equivalent to x prime plus y prime. We already know that if x is equivalent to x prime modulo n, then x equals x prime plus kn for some integer k. If y is equivalent to y prime modulo n, then y equals y prime plus ln for some integer l. So x plus y minus x prime plus y prime is k plus l times n, which is a multiple of n, which shows us that x plus y and x prime plus y prime are equivalent modulo n. This gives the result. Okay, so notice we've already done all the hard lifting. If you remember, about a month ago, we proved this thing called the fundamental theorem of modular arithmetic that makes all of this work. So now we're going to do something a bit more complicated. We're going to consider the following operation. Let's let the set S be the integers cross the naturals. So that's pairs of numbers, the first of which is an integer, the second of which is a natural number. And we're going to define an equivalence class on this set S, where we say the pair AB is equivalent to the pair CD if and only if AD equals BC, or AD minus BC equals 0. Let's check that this is an equivalence relation. Let's check if it's reflexive. Is AB equivalent to AB? Well, it is, because if we replace A and B on the right-hand side, we see that the equation AB equals AB is true. Let's now prove symmetry. Assume that AB relates to CD. Then by definition, that means AD equals BC. We do a little arithmetic and move things around. Of course, that's the same thing as saying CB equals DA, which is the statement that CD relates to AB. Therefore, we've shown symmetry. Now, we want to do transitivity. Let's assume that AB relates to CD and CD relates to EF. The first relation tells us that AD equals BC. The second relation tells us that CF equals ED. Okay, let's take the equation AD equals BC, multiply both sides by F, and switch them around. We can, of course, do that. Note that CF equals ED. So on the left-hand side, we can replace this and get BED equals ADF, and then we can cancel the D's, and we get BE equals AF. And before we ask, do we know that we can cancel the D? Yes, we can. Remember, D was the second component of one of these vectors, and by definition, the second component is always a natural number, so it's not 0. Since we've gotten BE equals AF, that tells us that AB relates to EF, and we have proved transitivity. Since, as we have proved, this is an equivalence relation, the equivalence classes of this relation give rise to a partition. So now, we're going to define two particular operations that are going to look a little weird. They're going to be a little bit like plus and times, but we're going to write them with circles around them. So here's how we're going to define it. Given the equivalence class corresponding to AB and the equivalence class corresponding to CD, we're going to add these two equivalence classes and define that to be the equivalence class defined by the pair AD plus BC, comma BD. Similarly, if we take the class corresponding to AB and the class corresponding to CD, then when we multiply them in this funny way, we get the class corresponding to AC, comma, BD. Okay, note that we're defining operations on sets, in particular, sets that are equivalence classes under this equivalence relation. Okay, now let us show that these operations are well defined. Let's do it one by one. Let's do the plus one first. So let's assume that AB is equivalent to A prime B prime, and CD is equivalent to C prime D prime. The idea being that AB and A prime B prime are two different representatives of the same equivalence class. By definition, this is true only if AB prime equals A prime B, and of course CD relating to C prime D prime says CD prime equals C prime D. We want to show that AD plus BC, comma BD is equivalent to A prime D prime plus B prime C prime, comma B prime D prime. That's what it means to be well defined. But notice what that means is that equation becomes AD plus BC times B prime D prime is equal to A prime D prime plus B prime C prime times BD. Remember, when I have two pairs, no matter how complicated they are, the pairs are equivalent under the equivalence relation if the first component of the left times the second component on the right is equal to the first component on the right times the second component on the left. So now we just have this complicated equation. Let's just multiply everything out, hither and yon, and we get AB prime DD prime plus BB prime CD prime equals A prime B DD prime plus BB prime C prime D. Are those equal? Well, notice if I look at the first term on each side, each of them has a DD prime term, so I can ignore that, and what's left over is an AB prime on one side and an A prime B on the other side. But by assumption, those are equal because the pair AB is equivalent to the pair A prime B prime. Similarly, if we look at the last term on each side, both of them have a BB prime. We could ignore that, and we're left with CD prime on one side and C prime D on the other side. And again, by assumption, those are equal. Now let's prove that the multiplication, the circle star, is well defined. So let's assume that AB is equivalent to A prime B prime, CD is equivalent to C prime D prime, which again means AB prime equals A prime B, and CD prime equals C prime D. We want to show that the pair AC, comma BD is equivalent to A prime C prime, comma B prime D prime. But if we multiply that out, that's equivalent to the equation AB prime CD prime equals A prime B C prime D. Remember, Equivalent means the first component on the left times the second component on the right equals the first component on the right times the second component on the left. Now we have 4 terms on one side equals 4 terms on the other side, but if you break them up into the ABs and the CDs, you see that exactly under the assumptions that we made, these are equal. Okay, so this looks like a really complicated thing. What are we really doing here? Well, you might have noticed this already, but if not, let me point this out. If I think of the pair AB as the fraction A over B, and I were to say, let's go back to school from years ago, how do I add the fraction A over B plus C over D? Well, we put that over the common denominator BD, and we end up with a numerator, AD plus BC. That is exactly the definition of addition, our little addition with a circle around it, that we made before. When we add these two pairs together, we get this other complicated pair. Similarly, when I multiply fractions, that's even easier. I just multiply the numerators, and I multiply the denominators. So what have we really done? We've taken a set S, which is Z cross N. We've defined an equivalence relation on that. What does that equivalence relation mean? That means that we have two fractions that are equal as numbers, although they may not be in lowest terms or something like that. And we've shown that addition and multiplication is well defined with respect to that partition. This is something we've all known for years, but we've actually just proved this, that addition and multiplication of fractions, the way we've defined it here, makes sense and gives us the rules that we all know and love. Okay, I'll stop there.